So make sure in this next discussion you remember that capacitance does not depend on Q or delta V. It depends on geometry and materials. No matter what, the capacitance, unless you have a variable capacitor, if you got one capacitor, this is going to be a constant. If this goes up, then this goes up right here. If this, by contrast, goes down, if you drain charge off of it, the delta V across it will go down. And vice versa. You can change the voltage, that'll change the charge. So very important thing to understand, though, is that the capacitance does not depend on Q or delta V. It depends on geometry and materials. Let's start with the geometry aspect of this, and you'll see what I mean. So let's deal with some different geometries, and we can actually derive the capacitance for very specific geometries, the first one being for a parallel plate capacitor. So let's go ahead and draw a parallel plate capacitor right here. What I've got is a plate of area A, okay? And I've got its other plate right over here. And these are a distance, and this is of course A2, I'm not even going to include that. They're a distance D apart. D from there to there, a distance D apart. So how do we, just from this, and by the way, there's a vacuum in here. You'll see why that matters later. Vacuum in between them. So this is a conductor right over here. These are both conducting plates. Right there is a conductor too. So how do we figure out the capacitance just from this? Well, let's use the definition of capacitance to figure this out. Definition, caps are quite overvalued. Well, let's maybe put some charge on here. And here's our charge. And of course, this one will have the opposite charge. Now, you can't see the front of this face, so we're going to basically be able to see through this plate. What we're looking at is the back of the plate. It's got the same amount of charge on it. And this is, we'll call this charge amount Q. Again, we don't have to have the sign or worry about the sign right now in the conventions of the capacitor world to just use positive Q. And we want to figure out what these two things are, what the ratio between Q and delta V is, and then that'll give us the capacitance of this thing. So, well, what is delta V? Well, let me give you a hint. There's going to be an E field in here. Let me use a different color for that. There's going to be an E field in here. I'm trying to draw three-dimensionally here. There's an E field caused by these charges. E, what's the magnitude of that? Well, being a conductor right here, and again, you got to be careful here because you might think, oh, it's two conductors, I've got to add sigma over epsilon naught plus sigma over epsilon naught. You actually don't. This is to just avoid confusing you. It's more like the situation when you have a non-conductor, because in this situation, there's actually no charge on the back of this thing. It's all been sucked to this side. There's no charge on the back of this thing. It's all been sucked to the front there that we're actually seeing through this somehow. So it's all here. So you can just say, well, the field here is going to be sigma over epsilon naught, where sigma, so let's go ahead and just get more specific here. Q is, what is delta V? Well, because we don't have to worry about the sign of it, delta V is negative ed, but again, I don't care about the sign of it, so I'm just going to use ED, ed. Again, everything's just the magnitude. Love capacitors, so easy. Well, what is E? So Q over ED is going to be, well, what's E? Well, because E is sigma over epsilon naught, this will be Q over, E is sigma over epsilon naught times D. And what is sigma? Well, this will be Q over sigma is just, by definition, it's the charge over the area A. Again, the area A is the area of one plate. Just one plate right there. And this is again over epsilon naught times D. So cancel, cancel. When we're done, the capacitance of a parallel plate capacitor is equal to, I'm going to write it like this, epsilon naught times A over D. Here it is right there. Now this makes a lot of good sense. And let's talk about why this makes so much sense. If I had a bigger area here, would it be easier for charge to move on? Sure it would. It'd just be like you have a bigger field. You got a bunch of cows. You want to put them in a pen. If the pen is much, much bigger, you can shove a whole lot more cows in the pen. And now why is it that D is here? Now let me ask you this. Here are my two capacitor plates, like here, that I've been demonstrating with. Now, if I've got a bunch of positive charges on this side, a bunch of negative charges on this side, if I just have this with the positive charges, that's not very happy, because these positive charges want to get a heck away from each other. This is a relatively high energy situation if this is all charged with positive charges. However, if I take this negatively charged thing and bring it really near, now it's like, oh yeah, this is much more stable. I'm right next to my negative buddies. I can hang out here for a long time. In fact, the closer these two are, the more stable. They can't touch, but the more closer they are, the more stable the situation. So you want this D really, really tiny, and you can get a whole lot of charge on there, because it's the closer they are, you can get them so they feel like they're back home on their atoms. Now you can't get them that close, but you can get them pretty darn close. So notice that the ratio, the more area that these plates have, the bigger the capacitance. The closer together, the smaller D is, the bigger the capacitance. And our constant in front, epsilon naught, don't forget that. But other than that, it's a completely conceptual derivation or equation. A over D times epsilon naught is the capacitance. Again, this is only for a parallel plate capacitor. Different geometries will have different equations for the capacitance. And also, if I have different materials, in other words, instead of a vacuum in here, if I put something else in there, that will also change the capacitance in a very interesting way, as we will see. So our final result, the capacitance of a parallel plate capacitor is epsilon naught times A over D. The bigger the area, the bigger the capacitance. And the smaller the distance between the plates, the bigger the capacitance. In other words, the more charge it can hold per volt of difference.